Welcome. This is a new lecture on measures of positions. Now, measures of positions is a way to look at a sample that you would see individual trees as opposed to seeing the whole forest. The idea is that you could possibly determine the position of an individual data entry in the sample, that data entry be. So we have three types of measures of position, or three measures of position. One of them is the rank, which is the measure that we would use on smaller samples. Another one would be percentile, or a percentile rank, as it's called. And the third one would be a z-value, which we will introduce a little bit later. So the rank is relatively easy measure to understand. For example, if you have 7 pieces of data here, 8 pieces of data, excuse me, here, the rank would be determined in ascending order by default. So for example, I have here 22, 23, 31, 49, 63, 65, 89, 79. And so the rank of the data entry 63 would be 5. Because it's a fifth item, the data entry in this sample going from the bottom up. And that is not necessarily always the order we would follow. For sometimes we have optimal order, the order that would be relative to what the data is about. So for example, I have a group of students here taking calculus tests, and the first student scored 95%, second 91%, and on. So in this particular case, I would rank from the top down. Again, default rank is from bottom up, but sometimes you could also rank in a different order. Sometimes you have a problem that a couple of data entry have the same value, like 91, 91. In that case, rank is determined by averaging the positions. So this would be, both of those items would be at the position 2 and 3. So we would average that, and would be 2 plus 3 divided by 2, and there will be 2.5 rank for both of them. That's a convention. So this is in case you have 3 of them, you average 3, so there will be a position. If there is another 91 here, there will be position 3 for all 3 of them, and then there would be nobody on the rank 2 and nobody on the rank 4, and the rest of them just continues the way it is. Right, so this is the convention how we use for ranking. Percentile is calculated slightly different. The idea of percentile would be that a percentile would divide the sample itself in terms of frequency, not in terms of a range, but in terms of frequency would divide sample into 2 parts. So for example, if I'm talking about percentile, there will be 65th percentile. Then that would mean that the sample would be divided into 2 parts. In one part of the sample, we would have 65% of the sample, and in another part of the sample, we would have 35% of the sample. That's the idea. Again, this is not about the range. My picture might look like it's about range. It's not about the range, it's about the frequency of the sample, of the data entries. So 35% of them would be in this part of the sample, and 65 below. So 65 indicates how much is below. Okay, we have a standard formula that we're gonna use, and it's not a standard formula for everybody. So there is a different kind of formula that is used depending in which region of the world you are, or even the United States Bureau for Standards and Measure uses a slightly different version. But in case of a large sample, when percentage would be calculated for a large sample, then it would be pretty much the same result. You might have seen that before in reports of SAT scores when they are reporting that in terms of a percentile, because there is a huge number of people taking SAT tests, and instead of telling you what rank you have in that test, which could be in tens of thousands, then you would get an information about percentile. So if this says percentile is 65, that means that you score better than 65% of the people, while there is a 35% of the tests that are better than yours. So that's the idea. So how do we calculate by using a formula? Well, for example, 74, which is a rank 7 here, we can calculate the percentile by counting how many items are below, and that number below would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So we would use 9. Then we add 0.5. Now that's for the purpose that we need to count this 74 somewhere. So we're going to count in a way half above and half below. And then we divide that with the whole frequency of the sample, the size of the sample, which is 16. And when we do that, my calculator says that this would be 9.5 divided with 16, and that's have to approximate to a nearest percentage. So this would be approximately 59 percentile of the sample. I'm using notation here of percent. 0.59 is 59%, but percentile is expressed as an ordinal number. So the ordinal numbers are the numbers first, second, third, fourth, fifth, as opposed to cardinal number, which would be 1, 2, 3, 4, 5, and so on. So we have 59 percentile. Again, it's expressed in terms of a percentage, although it is not set percentage. We would refer to that as 59 percentile. Also, the convention is that percentile is never expressed as 100. So it's only from 0 till 99. Okay, so I have another one, calculated data entry 49, 3 below, plus 0.5 divided with 16, and then multiply with 100 to get a percentage. And the result of that calculation is 22. You can check that with a calculator. So 3.5 divided with 16, and we have to round that to 22%. 0.21875, 0.22, or 22%. So that's how we get percentile. You can also get a rank from a percentile, and the following would be the formula to calculate the rank from the percentile. It will be a calculation that will be approximation. For example, you can see here that there's a lots of percentile are not here. We don't have a 54, 55, 56, 57, 58 percentile. So if I look for something like that, I would definitely find an approximation that could be 74, maybe 70, right? So if we are using this formula to find the rank from the percentile, it will be from the bottom up, because percentile is always from the bottom up. The 1 percentile means it's very bottom of the sample. 2 percentile, 3 percentile, that's at the bottom of the sample. 95 percentile mean at the top of the sample. So this formula, how it is used, So you use a percentile that you're interested in. You might be interested in 30th percentile, like I calculated here, 30th percentile. So you multiply the size of the sample times the percentile, so that would be 16 times 30, and then divide with the 100. So this is to eliminate basically percentile as an integer, as a whole number. So this is the same as if you calculate 16 times 0.3 or 0.30. If you do that, you get 4.8, and then you look from the bottom up for the fifth item in the sample, fifth, because the rank cannot be a 4.8 unless there are, of course, some averages. So we round to the nearest integer, which is the fifth, and then count, and you're gonna have 1, 2, 3, 4, 5. So 55 is the 30th percentile of the sample. Again, it's actually 28th percentile from our previous calculation. So this is approximation. The problem, of course, is that our sample is very small. So this would be no issue in case of a large sample, which is the case when we are actually calculating percentile. We can do one more calculation. So for example, what would be the 50th percentile of the sample? So the same calculation is done again. 16 times 50 divided with 100, and then rounded to the nearest integer. So my calculator says this would be 8 exactly, no approximation this time. And if I count 8 items from the bottom up, I get 1, 2, 3, 4, 5, 6, 7, 8. 68. You see, you could easily go with 70 because it's also, this one is actually 47% rather than 50. So the calculation is approximation. 70 could be possible. Next one. As a matter of fact, 50th percentile, which should divide the sample into 8 and 8. 50 and 50%. So again, the confusion here could be because we are really using approximation, and we do not use percentile rank as a measure for a position in small sample. This is a small sample, okay? So this is one thing to remember. There are some distinguished percentile we have a special name for. They're called quartiles. So 25th percentile is a quartile number 1, or the first quartile. 50th percentile is quartile number 2, or the second quartile, also called median. Median should divide the sample into 50-50. 75th percentile is called third quartile, quartile 3. And the difference between the 75th and 25th percentile is called interquartile range, as opposed to range, which would be a maximum minus the minimum. But if you subtract the quartile number 3 and quartile number 1, you get interquartile range. The rule for finding the quartiles is very simple. We will use the rule that is in accordance to Texas Instrument Calculator 83 and 84. For example, I have here students in statistics class in terms of their height in inches. And the first of all, this needs to be sorted. The data is sorted here. Once the data is sorted, you have the bottom half of the sample and the top half of the sample. If the sample has even number of items. If the sample has an odd number of items, then the middle one would be immediately quartile 2, or the median. That item would be then thrown out to the sample to divide the rest of the sample into top and bottom half, like it is here. So in this particular case, since we have the even number of things, we would look for the lowest item in the top half and the highest item in the bottom half, the two in the middle, 66 and 65, and that will be determined immediately as the median or a quartile 2. This was not the middle item in the sample, so the sample is already naturally divided in the top and bottom half. Then we would use the median of the bottom half. That would be the average of 62 and 61, since this is the even number of items in the bottom half, 12, so you go for 6 and 7 from either side, 2 in the middle, and then you calculate the average, and that will be the quartile 1. So quartile 1 is the median of the bottom half. And the same thing for the top half. The top half has 2 in the middle, so the median of the top half of the sample would be the average of 72 and 71, and that would be 71 and a half. And now, since you have the first, second, third quartile, you have a first and third quartile, you can calculate interquartile range by subtracting these two, and if you subtract 71.5 and 61.5, you end up with 10. Okay, now the 5 numbers, that would be minimum, quartile 1, median, quartile 3, and maximum. All easy to find. We will call this 5-point summary. These numbers you can put a comma in between if you're not comfortable with dashes, but these 5 numbers are called 5-point summary. If we use them to make a box and whisker diagram, also often called colloquially box plot. Box plot. First of all, of course, you have to establish some kind of scale. It has to be proportional. So I would use 10 for the scale, so it would be 40, I guess. It would start with 40. Then we would have, I should probably start it a little bit lower. So we will have 40. Then we would have 50. My scale is not really all that great. You should, of course, use a ruler. Then we would have 60. 70. Now, looking at this, I really should amend the scale. So my 50 and 40 should be much lower. Again, this is not to be done with the bare hand, and in a sense that I'm doing right now. You should actually use a ruler for that, because the graph, the box plot, ought to be diagram, ought to be chart, ought to be precise. We can change this a little bit just to make it look better, but again, you should use a ruler. Then we should have 80, probably somewhere here. And I guess I need 90 as well. Right. And then you start. Minimum is the left tail. The box open and closes from the first to the third quartile. 61.5, 71.5. The right end should be at the maximum, or right tail. In the middle of the box, we put one vertical line segment where the median should be. 65.5 is slightly closer to 61.5, so this should be a little shorter than this, which would be 6. So this is 4, and this is 6, the difference between the median and the third quartile. So it should look like that on the graph. My graph, of course, is more precise, so I don't really need this measured on the scale. The box plot has been done here by computer, so this is precise. You could also do that vertically. So sometimes box plots you can see in the media would be looking like this. Doesn't have to have tell as pronounced as this one, could be much less, but sometimes they look like this. I guess this would be my depiction of the box plot I have here. If there is a scale here that's visible, you should probably have that. If not, then you can write the numbers here at the edge of a box plot, like this would be 85, 71.5, 65.5, 61.5, and 45. Again, scale ought to be visible. So this particular line segment is 16.5 long. 16.5 long. The interquartile range, the difference of the quartile 3 and quartile 1 is only 10. So this line segment ought to look significantly bigger than 10, right? And this part here is 13.5. So it should definitely look something between this, should be longer than this part and shorter than this part. Your calculator can help you do that. So if you use your calculator, you would first put your data in the table in a calculator. It's called lists. List 1, I have them here. All of those numbers in the sample. Will take some time, of course, to make that input, but I have them in the list 1. Now, if you want to make a statistical plot, you have to organize that. So you use the statistical plot option here, which is blue option, so it's second Y, and then you have to turn the plot on. So you can use one of the 3 plots. So the 2 and 3 are turned off here, and the first one is turned on, but you can easily do that with just entering the plot and then turn it on or off. So you move that with the arrow, and then turn it, this would, press enter, turn it off, move it to on, turn it on, and that's it. You want to have one plot on the screen rather than 2 or 3 most of the time. Then you choose the type of a plot. The type of a plot you have here is a box and whisker diagram with outliers and box and whisker diagram without outliers, which we are going to do the without outlier, and then I'm going to show you later on about the outliers. And then you press enter. You have to tell your calculator where the data is. So I have it in list 1, so this is by default. You get a blue option here, second list 1. So if I need to press that, I'll do that this way. And then the frequency list, if you have a frequency list, I don't have, and then choose the color. And that's pretty much it. You also have to adjust the window. Window has to be adjusted. The scale to be, I already chosen the scale to be between 40 and 90, right? So it's 40 for X minimum, 90 for X maximum. Scale, you can use 5 or 10 or 1 or anything else you like. That will be just the down there visible on the scale. It will be notches on the X-axis. Why it's irrelevant here, it's not important. You can choose anything you like. You definitely want to choose something above 0, because if you choose 0, you will have the X-axis through your if you choose something less than 0, you'll have an X-axis through your screen, which is going to clog or mess up your plot. So choose 0 or something above 0, and then Y maximum, of course, bigger than that. And that's pretty much it. Now you can press graph, and you will have your box plot. Okay, so again, you can trace this. The trace starts with median, and then you can move it left, and you get a quartile 1 minimum. Down there it's the value, so 45, and quartile 3, 71.5, and the maximum. Again, in agreement to what we were already calculating. Outliers. Outliers in the sample are clearly defined, and the way they are defined is by using the bounds for the outliers. So it's not an opinion. You can look at the sample and say, okay, maybe 85 is outlier because it's so much taller than the rest of the students. The next closest student is 75 inches tall, which is 6'3", while this guy is 10 inches taller than 75. So that looks like some tall basketball player. But we will see that this is actually not an outlier in our definition of outlier. And then outlier, you could possibly assume they might be 45 as well. Okay, this is again not an opinion. There is the formula for the upper bound. If you pass the upper bound, you have an outlier. Lower bound. If you pass the lower bound, you have an outlier. So how is that calculated? You use a quartile 3, which is in our case 61.5. And then you add 1.5 of interquartile range, which is like a 150%, right? 1.5 of interquartile range. In our case, interquartile range was 10. That will give you the bound for the outlier. So when you add this up, you end up with 86.5. That is the upper bound for an outlier. Again, this would be 15, of course. 15 plus 61.5 is 86.5. The upper bound for the outlier would be 86.5. There is nobody in this sample that is taller than 86.5. So therefore, there is no outlier on that upper end. The same thing, not the same formula, of course, you do for the lower bound. Lower bound would be quartile 1. Okay, excuse me, I made a mistake here. I should have said that the quartile 3 is 71.5. I just noticed that. My calculation is right? 71.5 plus 15 is indeed 86.5. The lower bound would be quartile 1. Now that is 61.5. You have to be careful here, of course. And then you subtract 1.5 times the interquartile range, which is 10. So we get 61.5 minus 15. In this case, we get 46.5. That's the lower bound for the outlier. Anything below that would be outlier. So in our case, this data entry 45 is below 46.5, and that's the outlier, and the only outlier in the sample. You could have more than one outlier. It could be on the top end, it could be on the bottom end, it could be on both ends. But in our case, there is only 45. Okay, you can also check that with the Texas Instrument calculator, which uses the same formula. And so if I want to modify that, I'll probably go for the statistical plot, the one with the outliers. So now this is this one. It will give you an option again, the same as before, what list the data is in. And this time we're also going to give you the option to mark the outlier. You can use either a dot or a small dot, bigger dot, plus, or a little square. We're going to keep the default little square. And then graph again. And this time you can see the box plot. The outlier is noted separately. So this is 45. You can trace them, see that. 45 is the minimum, still the minimum. The tail now starts at the next item in the sample, which is in this case 50 in our sample. And then the quartile 1, median, quartile 3 did not change, nor it changed the maximum. So 5 point summary has not changed. Minimum, quartile 1, quartile 2, or the median, quartile 3, and maximum still the same. It's just the plot is slightly different because now we are marking an outlier separately outside the tail in a box plot. Okay, the next thing I want to talk about it is another measure of position, which we call a z-score. Now z-score can be calculated both for sample and a population. So it's a measure that we use both for sample and a population. It's calculated in the same formula, or similar formula, I should say. In case of a sample, we are calculating z value by subtracting any x value minus the mean of the sample and dividing with standard deviation. So which means that every item in the sample, the x value, has a z-score, z-value, z-score, or a z-value. So in our sample before, The mean of the sample is 65.29. You can calculate it easily, but just averaging everything in the sample. The sample standard deviation is 8.83. So you can calculate that by either formula that we have seen before, or you can use your calculator. So edit the data is already in the list one, so I don't need to do that. I'm going to calculate one variable statistics. In one variable statistics, I want to do that for the list one, of course. If you have frequency list, you should put that here. If not, just go and calculate. Enter will calculate everything you need to know now. The mean 65.29, I used to decimal approximation. Sum of x's and x squared that we use for the calculation of standard deviation is not needed. Here is a standard deviation, 8.83. Now, of course, there is a population standard deviation in case you have a population. The size of the sample is 24, minimum is 45, gives you the quartile 1, quartile 2 or median, quartile 3 and maximum. But I need the first one, which is here on the screen, 8.83. I'm approximating that, so that's sample standard deviation. So when you do this calculation, for the item 72, z-score of this item would be 75. Z-score of 75 will be 75 minus the mean. It's a 65.29. Divide with the sample standard deviation 8.83. This is approximation. 2 decimal approximation. Z-score is approximately 1.1 if I use 2 decimal approximation, right? It's going to be 1.1 and then it's 10, so that of course is 1.1. So the approximation would be 1.1. What does it tell you? It tells you how many standard deviation you're above the mean of the sample. The mean of the sample, the average height of the students, of the group of 24 students, is 65.29 inches. And the student whose height is 75 inches, his height is 1.1 standard deviation above the height, that is the average height of the class. So if you multiply this one with 1.1 and add to this number, you get 75. You can check that with your calculator, of course. That's just a reverse of the formula. So 65.29 plus 1.1 times 8.83. So what I'm doing here, I am multiplying standard deviation with 1.1 and adding that to the mean. And I'm getting something very close to 75. Of course, there are some little mistake because of the nature of approximations that we did. So that's a reverse formula. So if you want to calculate the x value from the z value, z-score, you multiply z value times the standard deviation, add to the mean. For example, if somebody tells you that your IQ is 1.7, z-score, that would mean the IQ tests are with a mean of 100 and with the standard deviation of 15, usually. Sometimes 16, but usually 15. So you need to multiply the z-score times standard deviation. So the z-score, z-value times standard deviation, and you add that to the mean. And if you do this calculation, 100 plus 1.7 times 15, we get your IQ test result is 125.5. It's usually not reported as a decimal. I would be like probably rounded to 126. Okay, that's the meaning of z-score. You got a 1.7 standard deviation above the mean. It could be also below. So for example, in this particular sample, I have the 52. The item in the sample is below the mean. The mean is 65.29. So the z-value will turn out to be negative. 52 minus the mean. So I'm using again this formula. This formula here. This will be for the second one will be for the population. We are using sample formula here. The x value 52 minus the average 65.29 divided with standard deviation 8.83, numbers calculated previously, and you do that, you end up with negative 1.505. So obviously the student whose height is 52 inches would be below the mean of the sample, and it's approximately 1.5 standard deviations below the mean of the sample. That's the meaning of z-score, z-value. Again, another measure of position, and this measure of position is something we're going to use further on. Okay, beyond the regular homework, I have 3 or 4 more extra credit problems for you in case you were not challenged with the homework. You can do a little more work here. The number 4 is kind of interesting. We would, in the list of the countries by infant mortality rate, which is one of the measure of how good the healthcare system of the country is, and it's on Wikipedia, you can check it out, and you would get various data. So the first one is by using the World Bank data, and it's not sorted, it's in alphabetic order sorted, but not by numbers. So then you have another one by OECD and another one by CIA. So you can use either one you like and find out, or all 3, and find out in this data what percentile and what rank is the United States. So we have United States somewhere in this list. It's something interesting. So infant child mortality now it's 5.3. A year ago 5.7. Now it's 5.3. So 5.3 per 100,000 children will die at birth. And it's interesting to compare to the other countries. Of course, some are much worse, like Venezuela here is worse, but some are better. This is some territory of France. And you might want to check this out. Okay, so this would be an extra homework beyond the regular homework. So this was a lecture on measures of position. Of course, you need to do the homework to reinforce this what I was talking. Okay, I'll see you the next time. All right.